Hello everyone, my name is ANISH. I'm a third year student from IT Roorkee, Engineering Physics branch. Today I'm going to talk about a topic which is fast Fourier transform over finite fields and its application in Reed-Solomon codes. So let's move on. Basically before talking about Reed-Solomon code, a Reed-Solomon code is a error correcting code. So let's just talk about firstly about error correcting codes. So error correcting codes are nothing but codes which resolve errors in the corrected message. And this message and the error correcting codes combinedly forms a code word. So error correcting code is nothing but a redundant bit. So supposedly this is a message 1010. This is our message, and this one is a redundant bit. So this is used to solve error in this message. So we have four messages here, one, two, three, four. Each is assigned 0001. So in binary, we are talking about here binary codes. So automatically the size of our code becomes 2 to the power of 2, which is 2 or 4. And the block length of this code is 5. Yeah. So a block code is represented as n comma k, where n is the block length and k is used to compute the size of the code. So yeah, let's move on to Reed-Solomon codes. So Reed-Solomon codes are cyclic uh, block error correcting codes. So cyclic because they come under finite fields. Uh, so this a Reed-Solomon code is constructed over finite field of dimension q. So this is read as finite field as of dimension q, and the block length of the code should be equal to q minus 1. This is due to the like the due to the multiplicative group of the finite fields. So the multiplicative identity of each element should be equal to the dimension of multiplicative group. So that's where this condition comes. So FQ is a extension finite field with dimension q, where q is p to the power of k. So a field dimension should be a prime power. So in a RS code, we have n minus k parity symbols. So parity is like to change a sign. So from 0, 1 and 1 to 0. So these are the parity symbols, and the k spots are used for the message symbols. So both combined form a code word of length n. Yeah. So a good example of this is we have some message supposedly with data symbols ABCD, and now due to some noise or some external factor, the message get corrupted and it changes to supposedly some XYCD. So now the Reed-Solomon error correcting code, what does is it first assign a redundant symbol, like it assign for each block it assign a redundant symbol ENF, and with this ENF, it start to detect the position of error and the error value. So this ENF is used to correct this message. So we will be developing Reed-Solomon code algorithm over a finite field of dimension 2 to the power of n, where k by n is greater than half and n minus k to the power of 2. So we will be developing encoding and decoding algorithm for a finite field of dimension 2 to the power of n. So firstly, let's understand what is Fourier transform over an extension finite field. So first, we will start with a discrete Fourier transform. That's how we end up in fast Fourier transform. So for a discrete Fourier transform over a ring, so supposedly I have a R ring, and I have a principal and a root of unity. So I'll write omega n equal to 1. And as we know, for a cyclic finite for a finite field, the elements should add up to 0. So that is what it is written. So omega 0, omega 1 till omega n minus 1. It should all sum to 0. So now talking about what is the discrete Fourier transform over a ring. So it is Fk equal to summation 0 to n minus 1 omega to the power of jk Vj. So Vj is what is the original basis, and Fk is the what is our Fourier basis. So just taking matrix of um, roots of unity and multiplying it with the original basis, we can get the Fourier basis. So for a, so we were talking about a ring. So by from special cases for like complex field, our omega become e to the power of 2 pi I divided by n. So for complex field, our root of unity is e to the power of 2 pi I divided by n. So we will just substitute omega here. Instead of omega, we will substitute this and we will get this. So this is which we are familiar with. So this is our discrete Fourier transform in complex for complex numbers. So moving on. Um, so let's talk about for finite fields. So for finite fields, we have sorry, we take Galois field, which is we will assume f is equal to GFQ, where Q is a prime power, and as we know, as we discussed before, the size of the multiplicative group of a Galois field should be divisible by the multiplicative order of each element. So that's why n divides q minus 1. So moreover, for an extension finite field, we have our n should divide q to the power of m minus 1, where m is some arbitrary number, integer arbitrary number. So then there will exist a Fourier transform of length n over extension finite field of f of dimension q to the power of n. Yeah, so moving on to get the inverse Fourier transform. Yeah, so for inverse Fourier transform, our formula becomes Vj, which is we are retrieving our original basis from the Fourier basis. We have uh, omega inverse of jk and 1 by n here. So the proof is very trivial. We have to just in this formula we have to just add in another summation element, supposedly L or like any element, and we will sum it, and we will get an extra omega kl, which will sum to 0, and which will give to 2 pi divided by n. So this will, like, the proof is trivial. You have to just add a new summation within a new element. Yeah. So moving on. Yeah. So where is FFT? So FFT is nothing but we are using to compute discrete Fourier transform by computing each element. The time complexity is it takes is O n square. But fast Fourier transform, the algorithms have complexity of O n log n. So O n log n is faster. So some example are Cooley-Tukey algorithms, which are used for only some certain dimension of finite fields. So moving on, we have to define a new polynomial basis to extend to like compute a fast of Fourier transform. So we will assign a new polynomial basis. So we will take a vector in the basis of f infinite field of dimension 2 to the power of n. Yeah, so we have each element which belongs to the finite field of dimension 2 to the power of n, which is linearly independent over the dimension of 2. So we will get a subspace for f f2 to the power f subscript 2 to the power of m. So we can get the subspace for dimension k, which is represented here, where ij we represent I naught I1 till I of k minus 1 is can only be assigned 0 or 1. So which is our dimension 2 finite field. So in this, so we have total 2 to the power of n minus 1 elements in this subspace. Like in in total 2 to the power dimension of finite field, we have 2 to the power of m minus 1 elements. So for our subspace of dimension k, we have 2 to the power of k minus 1. So moving on, I'll define a subspace polynomial. So the polynomial, subspace polynomial in a finite field could be represented as Sk of x, which is the product of our all elements in the subspace Vk. So the degree of this subspace polynomial would be 2 to the power of k, because we have 2 to the power of k minus 1 elements, which so x will be multiplied that much times. Uh, so we sorry 2 to the power of k elements. Next, I'm gonna expand this form. So expanding this form, we will get a summation symbol here, and I will vary from 0 to k, and we have some coefficients here, which will belong to the finite field of dimension 2 to the power of n. Moving on, this subspace polynomial have some properties which have been like derived. You So this is sk x plus y equal to sk x plus sky, and xy is finite field over dimension 2 to the power of n. And also we have a recursion form for our subspace polynomial, which is this. Um, Moving on, we are just deriving a polynomial basis. So we got a subspace polynomial. Now we are going to define some basis, which we will work on, and then we will try to get a Fourier basis. So first, let us define a basis which we will be working on. Our polynomials will be working on. So uh, this is x bar g of x bar. So we choose a x bar as our basis, which is field over dimension of 2 to the power of m. So this is a polynomial of dimension 2 to the power of m, where we have a quotient space of x to the power of 2 to the power of n minus x. So we will define basis elements like this, such that our degree of elements is I. So by this, we have some clever techniques which we can use to manipulate and get a Fourier transform, which we will see. So moving on, so we have defined our basis. So now we can write a polynomial of degree x in our basis x bar, which is just a polynomial expansion. So now we will for fast Fourier transforms in finite field, we have to just evaluate for polynomials at certain points. So just evaluate. So if you have learned about the Galois theory, the Fourier transform, the convolution theorem just states that we have to just multiply two we have to just for a convenience, we have to just multiply two Fourier transform of a polynomial coefficients. So that is where it came from. So for compute a fast Fourier transform, we have to just evaluate polynomials. So we will start with we have defined a polynomial of degree h in basis x bar. So we will work only on dimension 2 to the power of k. And also, I have an additional point which I'll call beta, which is again a part of our polynomial field of dimension 2 to the power of n. So we will use a set of evaluation points, which is bk plus beta. So this is our set bk plus beta, which can be broken down into two cosets, which is bk minus 1 plus beta union bk minus 1 plus bk minus 1. This is a element which we defined previously. So there it is. Yeah, so this is a bk minus 1, which is originally the element k minus 1 element of a subspace bk minus 1, and of course the plus beta, which additional point which we have added. additional set of points. So there is one lemma. So for any beta is proposed is in dimension of finite field, and also there is an element of subspace Vk. We have this expression, so which we can further manipulate. So we can assume the bracket part to be g of I, so superscript g of I0. So and our I ranges from 0 to 2 to the power of k minus 1 minus 1. So by this algebraic manipulation, we just substitute gi 0 here, and we get d of power to the 2k minus 1. So I just want to point out here that we have gone from dimension 2 to the power of k to dimension of 2 to the power of k minus 2. So we have reduced by half. We have reduced our dimension by half. And yeah, so this also, so we have got this term as d of 0 to over dimension 2 to the power of k minus 1 of a plus beta. Now again, if I have to convert this bk minus 1 plus beta, I will again go through this step. So you can read this step and come up with the solution. Again, so here we have used the recursion form of our subspace polynomial. So bk minus 1 plus beta becomes sk minus 1 beta. And again, manipulating this, we can get here gi of 0 plus di plus 2k minus 1. So we will assume this bracket to be gi of 1. By assuming this gi of 1, we can again write in this form, which is a polynomial expansion form. So we will get d of, so we get a polynomial of the dimension of 2 to the power of k minus 1 of order 1, and the elements are a plus bk minus 1 plus beta. Okay. So what we have done is we have expressed our set of evaluation of points from this to this. So we have defined a polynomial of dimension 2 to the power of k to 2 to the power of k minus 1 and 2 to the power of k minus 1. So what we have done here. So for the first polynomial, so we have for the first polynomial we had gi of 0. So for like for dimension of 2 to the power of k minus 1, we have 2 to the power of k minus 1 coefficients, and so for that coefficients we have same number of additions and some multiplications to the rest of the to the power of excess. So for that uh, and for the second coset of polynomials, we have we had this gi plus gi of 0 plus di I plus 2 to the power of k minus 1. So we have to calculate each coefficients of this, which will take again a total of 2 to the power of k minus 1 additions, which we obtained in the previous one. So the one which we obtained for vk minus 1 plus beta. So in total, if you work out the recursion formula, both of this polynomial set till this set length become one. So it will come out to be the time complexity of both the set will come out to as 2 to the power of k log 2 to the power of k. So we have just arrived recursive approach uh, to find the Fourier transform in our extended finite field. So at last, as firstly I told you, the polynomial evaluation is what Fourier transform in a finite field is. So we have obtained a recursive approach to find a fast Fourier transform. Moving on, to calculate the inverse Fourier transform, we just do the backtracking of fast Fourier transform, which is we just reformulate a expression of recursion and coefficients. So instead of gi 0 plus di plus 2 to the power of k minus 1 equal to gi1. We have just gi0 plus gi1 equal to bi plus 2 to the power of k minus 1. And um, and for and for the coefficient we have gi0 plus again the same thing. So this is how you calculate the inverse Fourier transform. So moving on to our Deep-Solomon encoding algorithm. So this encoding algorithm will introduce us to O of n log n minus k time complexity, uh, where uh, where t is equal to n minus k and is a power of 2. So yeah, we will develop a time complexity of this at the end of this section. So first we will take a polynomial evaluation approach. So which is basically we take a message which is interpreted as a polynomial over this field which we have talked about before, and yeah, and the degree of this field is less than k, and the code word after the message is passed to the machine is this. So we will just evaluate our polynomial at n distinct points, which is just the fast Fourier transform. So by taking this, so we have this message from u0 to uk minus 1. So this k bits are a message, and this t length is our redundant bits. Like we are talking here about general fields, but if we have supposedly m equal to 1, then this would be just bits. So we have taken all the redundant vectors to be same, which is omega naught, and we will just apply the t point fast Fourier transform. So we have here t points, right? So which will give a code word b, which is this. So we can calculate a code word using just fast Fourier transform, where we have assumed all our redundant vectors to be omega naught. But this code word comes out to be not systematic, and it has a high time complexity. So we generate another method, which is a generator polynomial method, where we divide our v into n by t subvectors, where each vi is defined as this, and the choice of this subvector is just because we can represent a omega naught as inverse Fourier transform of this subvectors. Uh, just due to this fact, we have chosen vi to be this. So to omega naught the inverse Fourier transform of our all summation of our all subvectors, we have chosen this uh, specific vi, and here vi dot t vi 1 plus I dot t is elements. So these are all elements of vi. So moving on, calculating the time complexity of our encoding algo, we have so the so this previous lemma was a core transform for our proposed algorithm. So the main purpose was suppose every element of V naught is water parity symbol. So this parity symbol is added to each block of the other subvector to be the message symbol. We will so here we will just take the inverse Fourier transform from V1 Vnt till n by t minus 1. So we will exclude V0 here. So this will give here V dash 0. So V dash 0 is nothing but just we have added some parity symbols in our original messages. So this is what it represents, and then we just take the Fourier transform of this message, which gives us a systematic code word. which have a less time complexity than the polynomial evaluation approach. So for the so we have used n by t minus 1 times the inverse Fourier transform. So we have this term here, and we have at last we have used the fast Fourier transform. So for that we have the complexity this. So adding this, we get O of n log of n minus t. Uh, moving on to the decoding algorithm. So our G-Solomon decoding algorithm can be broken down into four steps. First is calculating the syndrome polynomial S of x, and second is the determination of the error locator polynomial by the Euclidean algorithm, which is lambda x. And third and fourth are the finding the error location and calculating the error values. So let's move on and let's see how the algorithm works. So first we're gonna have a receive vector. So after the machine processes it, we have a receive vector. So in this vector we have our our original message, which is u of wi, and some error pattern which we will call by ei. So our receive vector is addition of this both. So if ei is not equal to 0, then ri is a erroneous symbol. So if ei is not equal to 0, then this bit has this subvector has a error. So supposedly for we have b non-zero symbols, which is less than t by 2. We will assume a set of location of errors, which we will define by the defined by omega n. So we we can uniquely define our elements of u by omega n. So that's why we have chosen omega to choose to get our location of error. So we will have this set. So omega is belonging to the um, finite field of dimension 2 to the power n such that ei is not equal to 0. And we will define a error locator polynomial. So if this is a set of errors, so our error locator polynomial would be the subspace polynomial, right? So we will define lambda x equal to be the subspace polynomial of this error set. Nextly, mm, nextly we will define another polynomial which is r bar x to be r bar omega I equal to Rn. So we are just simplifying our approach to get some equation which we can evaluate to get our lambda x. We are just manipulating our equations and getting some additional polynomials so that we can calculate lambda x. So we will have we will let we will assume a polynomial r bar of x such that if we put omega I, we will get r of I. Okay, so if you multiply r of omega I into lambda of omega I, we will see something a good pattern here. So if omega x belongs to our error set, then it becomes 0, and if it belongs to the uh, to not like if it does not belong to the error set, then we will receive ri dot lambda of omega. So this gives us so if we try to get a general formula for this, we will get u of x dot lambda of x equal to r bar of x dot lambda of x times mod of x minus omega I. So we have seen this, right? X minus omega as a subspace polynomial for our omega I. So if we take a subspace polynomial for this omega I, we can write this as s of s or of dimension n x. Also, we can break down this mod by adding up some quotient. So we can write this as u of x dot lambda of x equal to r bar of x dot lambda x plus q dot q of x dot sm x. So we can just here evaluate this and find. We can use our Euclidean approach, Euclidean algorithm to evaluate lambda x by putting in Sn of x and r bar of x. But here we don't know about r bar of x. So what we will do is we will try to do some more substitution. So here we will use r bar of x equal to r naught of x plus xk, which we defined earlier, the our polynomial basis, and this is s of x. So this r naught of x is what we call our residual, and so if our residual is non-zero and there is no basically no error, so our s of x becomes zero, and we get r of x equal to u of x. Okay, and this s of x is what we call a syndrome polynomial. Now, some manipulations, uh, by manipulation I mean we are just dividing here by x of k by x, and we will get a Fourier formula, which is z naught of x equal to s of x lambda x plus q of st of x. And st of x is nothing but sn of x by xk of x. So we have just here done some manipulations to find a lambda x. So we will just use our extended Euclidean algorithm uh, for s st of x and s of x. Yeah, and for extended Euclidean algorithm, our remainder polynomial degree should be less than t by 2. So by this we can find our error locator polynomial. If we have find our error locator polynomial, then we can find the location of errors, which is just the roots of lambda x, as we have discussed here this thing. And also, the final step is to calculate the error value, which is nothing but u of omega I minus r bar of omega I, which if we take a formal derivative of this equation, then we will get this thing, which is q of omega I divided by lambda of omega I. By this we can also find the error value. Also to find our syndrome polynomial, we will just use uh, the assumed R of x here. We will run inverse Fourier transform over R of x here uh, for different values of omega. So we will get our syndrome polynomial. By this, we will get our the complexity of RF decoding. For for our first step, we get O of n log of n minus k for the first step. For the second step, we will get n minus k log square n minus k. And for the third step, which is location of error and error value, again we will get O of n log of n minus k, because we are just utilizing uh, we are just using this thing n by t times inverse Fourier transform, and then again using again a Fourier transform. Yeah, so by this we get a complexity of a decoding algorithm as O of n log of n minus k plus n minus k logs to n minus k. Yeah, so this was our reach element encoding and decoding algorithm. So this is like generally used uh, in computer hardware to if there is some error code error messages in our hardware, then this read element code is used. There are also different codes such as BCH codes or some different cyclic codes which are also used. But yeah, this is the uh, most used till date and the most oldest, I think so. So yeah, this was Reed-Solomon encoding and decoding algorithm by using FFT over finite fields. and thank you. Uh,